Heat Pump Association. Glad to have you here today and joining us. This is the International Ground Source Heat Pump month. We're trying to promote and celebrate that and bring awareness to it. So you'll see the logo here on our backdrop today. We've been promoting it all April, trying to get more people to have an awareness of it. So thank you for joining us, and hope you enjoy our presentation today. Slide here. Before I get started with our two presenters that we have today, I have a few announcements to make. And the next slide. Sorry, too many screens going on here this morning, causing me some confusion. As we get started on our announcements that we always like to make before the Dig Deepers, one of the things we want to bring out is this is our 4th Dig Deeper for the year, and we had a town hall earlier this month. And if you would like to be one of the speakers on our webinars, we do have opportunities for those, as well as advertisers. These recordings and sponsorship advertising stay on the recordings and will be promoted for future viewers that may watch the recorded presentations later. All you need to do is go to our website. We have a link for training and events, and there, if you click that, you'll find an abstract you can fill out, and you can send it over to us, and we'll put you on a list for future opportunities if you would like to participate with us on these Dig Deepers. We're getting a lot of good attendance on these, and they've been really enjoyed by everybody attending. The next announcement I have is our association just recently completed our annual 2025 conference in Champaign, Illinois. So if you didn't get to join us at that one, it was a really good conference. And we have planned the next one already, and we are getting some preliminary announcements out about it. So our next 2026 annual conference is going to be at the Ameristar Casino in St. Charles, Missouri. So that will be April 14th through the 16th. So maybe mark it on your calendar and start making tentative plans for it. If you watch our website, we have a link on the website for those announcements about the conferences. So stay tuned to that. There'll be additional information posted as we are getting closer to those dates. We also want to talk about another opportunity we've got coming up. We have a sponsorship with the International Energy Association Heat Pump Conference, which is going to be held in Hofburg, Vienna, in May 26th through the 29th. So we work with a lot of technical organizations about technical related materials to help develop and encourage the growth of the industry. And so IXPA will be participating with that conference in 2026 as well. So if you are interested in that, you can check it out and certainly look into attending or reading the papers afterwards. In addition, we have our Geo Outlook magazine, which we're really excited to have back this year and promoting. We are still accepting advertising and articles for the July issue through June 1st. So special pricing for benefactors and renewing business members are available. It is published by BPN magazines, which are very popular with several industry-related trade magazines like the ACR News, Engineer News, and so forth. They have a pretty large reach of advertisers, over 50,000 plus and growing. So if you're interested in participating in that magazine, we would love to incorporate you with us on that. It's going to be a good issue coming up. So contact us at info@ixpa.org for more details. We also have been working on some IXPA databases as our industry grows, and there's a lot of interest in the technology. There are lots of people looking for more details about where can they find projects and jobs and so forth. So we are building databases on our website, and if you're member and have some projects and credentials that you would like to add to that database. If you've not done it yet, we certainly want to encourage you to do so. We're getting this information to help everybody find what they're looking for. So there's links on the website here shown, which you can click, and there should be inputs that you can add the details for us on there, and that would be very beneficial to us as well as outside general public folks who come to us looking for this kind of information. We're also providing CEUs and renewals through our website for our town halls and dig deepers and annual conferences. So if you would like CEUs for this webinar, please send a message while we're on this meeting to IGSPA. You can include your name and email, and we are providing these credits shown for the contact hours and certificates. So we'll certainly make that available. Just use the chat area, or you could use the Q&A area if needed to do so. If you're joining us later after this live broadcast, there will be a webinar code you would need to submit to us if you watch the webinar. So here's the code 2504TH6. That's an example you would use for the recordings and to get those CEU credits. If you're watching live, you won't need to do this. You can just send us the chat that you'd like the credit. For some housekeeping before we get to our speakers, we're going to ask that you would use the chat or the Q&A area during the webinar, and we will try to get to those messages today as we can. Hopefully time allows us to get to all of them. If we get more than we can, we'll try to pick up those questions and send you some answers afterwards. So please consider, as we go through the presentation with our speakers today, to submit your questions or Q&As that way. And we will also be recording this session, so everything will be recorded. So attendees, if you're having any kind of difficulties using the Q&A area or the chats, this is a good overview of how you can hopefully overcome that. So just click on the dialog box to the right or to the left, and hopefully that will let you get in and provide those. If not, you could raise your hand, click that raise hand icon, and we'll try to unmute your mic and let you voice your communication that way. And finally, the disclaimer and potential conflict of interest statement we need to read. The upcoming presentations represent the opinion of the presenters and does not represent of any official position or opinion or endorsement for products or services by IGSPA or its members. Our town halls and dig deepers are for member updates and communications on the latest information in the geothermal heat pump industry and are not meant to endorse one technology brand over another. It's the presenter's responsibility to disclose any conflict of interest or position that may arise in the content of the webinar. So we just need to put that out. And now I'll get to our bio introduction for our speakers. And so today we have with us as guests both Patrick Nortz and Greg Nortz. They are co-founders and owners of Otisco Engineering. Patrick is a co-inventor of a ground loop system developed in collaboration with his brother and business partner, Greg. He has a Bachelor of Science in Geological Water Resources, Hydrology from the Ohio University in Athens, and an MS in Agricultural Engineering from the Ohio State University in Columbus, Ohio. He has more than 35 years of experience in the environmental engineering, utilities, hydrologically, water resources and waste management, and on-site home sewage treatment systems. He's a certified professional geologist and professional engineer in Ohio and Minnesota. He's a comprehensive understanding of environmental systems, and he has experience spanning both regulatory and industrial settings, collaborating with multidisciplinary teams of scientists, architects, engineers, technicians, administrators, owners, or government officials. He's a skilled project manager, excelling in management scope, schedule, budget, personnel, and workflow. He's an experienced writer of proposals and grant applications, including lead author of 2 successful small businesses innovative research grant applications to the USDA for advancement of the Otisco ground loop system. And he's a membership in organizations like the International Ground Source Heat Pump Association, the Air and Waste Management Association, and the American Institute of Professional Geologists. And his brother, Greg Nortz, is also a co-founder. He is a co-inventor of the dual flow manifold and the Otisco ground loop system. He brings a unique blend of engineering experience and entrepreneurial vision to his work. He is a Bachelor of Mechanical Engineering from Cleveland State University and a Master of Business Administration from Clemson University. He's a seasoned mechanic with 45 years of experience on a proven track record of success in both technical innovation and business leadership. Greg is a registered professional engineer in 7 states like Ohio, Kentucky, Virginia, North Carolina, South Carolina, Georgia, and Florida. He's a certified HVAC contractor in Ohio, and he's recently completed IGSPA's Geo Designer course. His experience spans a wide range of mechanical engineering disciplines encompassing research, development, design, estimating, drawing creation, and specification writing. He's successfully managed and overseen installations of more than 50 building HVAC systems. Greg's technical expertise extends beyond geothermal systems. His R&D includes contributions to the design of pressure sensors, flow meters, temperature sensors, vibration and seismic control systems, on-site home sewage treatment systems, and microchip handling systems. Most notable of his contribution to development is a temperature sensor for the International Space Station's active thermal control system. His membership in organizations include the International Ground Source Heat Pump Association and the Ohio Society of Professional Engineers. So I want to welcome them both, and we'll let you take it over at this point.
Thank you. Give me a moment here and I'll share my screen and we'll get rolling with the presentation. Just one second.
I think I need to stop sharing my screen so you can do yours. Okay, we did. Good.
All right. I'm Pat Nortz. Sorry we wrote such a long bio. I didn't know that would last so long. But today we're here to present the aforementioned ground loop system that Otisco Engineering, via Greg and I, have come up with. And we want to cover not just our system, but kind of the background for what led us to where we've gone. So with that, I won't go through this. We've done all that, but we'll jump into the next slide. So this shows everything about geothermal systems. Well, a lot of stuff. We're not going to cover all this stuff. We're just going to cover the ground loop portion of it, which is depicted on the left side of this diagram. Our goal with what we've done and through this presentation is to provide a simplified ground loop installation approach. So here's the rest of the agenda. We're going to quick market overview, cover some of the installation technologies. We're going to get into the details of the Otisco ground loop system, and then we're going to show you some example installations and how we've evolved into what we come up with the Otisco ground loop system. And then we're going to summarize the benefits of the system and some other benefits that have arisen through our work over the years. So the market. So as most of you on this call know, geothermal's growing in the market. So according to this graph, which we admittedly pulled off the internet, shows $1.2 billion worth of geothermal heat pumps in 2020, and it's projected to grow at 11% a year. We estimated, based on some DOE report data that we looked at, there's approximately 20,000 U.S. residential installations per year. And as many of you know, and as this graph illustrates, the largest number of geothermal systems will be closed loop technology, which has been our focus. So here's a graphic showing some of the technologies out there for loops, not all ground loops. There's pond loops and then vertical ground loops, um, ground loop with a looped connector. There's horizontal collectors that are trenched in and drilled in, and all sorts of things. We'll cover a few of the vertical and horizontal ground source heat exchange installation methods on the following slides. So here's some photographs of vertical well installations. Kind of what led us to where you see what we're going with as we proceed through this presentation is we found that the vertical installations in particular have been quite disruptive to the landscape. So if you're doing a retrofit on a residential property, the homeowner doesn't typically want you to wreck their yard. Historically, the water well drillers were the ones installing the system, so they come in with their water well technology, the big drill rigs, and they would heavily impact the landscape on the property, disturbing the soils, leaving grout and cuttings and rutting all across a particular property. Typical 6-inch bore will produce spoils that will often cover the installation site in mud. So we were inspired by what we saw to try to do something better. And the same goes with the trench horizontal ground loop installations. A backhoe is often utilized to trench and backfill the ground loops and requires a significant amount of soil be moved, creating more work and increasing project cost. So back in 2013, we installed our first system, and these photos illustrate that. This was at a home in Central Ohio. We were able to pull a drill rig between the homes and a small rig, as shown in the center photo, and we were able to install, I think 5 bores was the design on that one, from one spot radially outward toward the back of the property. And as you can see, there's no impact on the ground other than at the manifold location to the property. What else did I want to get across? And yes, with that, end result is a more efficient and cost-saving installation. So now let's jump into what we've come up with, the Otisco ground loop system. So this figure illustrates our preferred system design, the Otisco ground loop system. Through the remainder of this presentation, we will drill into the details, pun intended. So the graphic here shows how we have the manifold in one location, and then with our design, 3 horizontally directionally drilled horizontal bores radially outward from the manifold. So with the Otisco's ground loop system, it's a tube and tube system. So we don't have the U-tube. It's a small diameter 3/4 inch tube inside of a 1 1/4 inch diameter tube. I'm saying tube, it's actually classified as pipe. So it's SDR11 pipe. And so what we were hopeful to show, we had the idea of doing the tube in the tube, aka coaxial tube. We wanted to demonstrate that we would get efficient heat transfer like the U-tube. We'd have pressure drop similar to the U-tube, and then we'd have flow equal through each loop. And so on these next slides, I'll get into that a little bit more. So this was this is an ongoing graph at our first installation where we have monitors set up. And so the question we had, that we hypothesized that the tube and tube loop would be similar to the U-tube with respect to heat transfer performance. So we put 2 of the loops on that installation I showed you in the few photos back with the small horizontal drill rig. We put a side-by-side U-tube and coaxial tube or tube and tube loops. And This is just one example, but we've seen this through all of the data that we've evaluated through the years. We've been able to verify the performance of the tube and tube versus the U-tube with respect to temperature on the side-by-side loops, about 16 feet apart. They're very similar. So the blow up shows you that these lines are almost on top of each other throughout the heating and cooling cycles. In this case, we're in the heating mode. So temperatures are within half a degree of each other in this example. So the other thing, we wanted to show that we could equalize flow through our manifold, which I haven't shown you all the details of that yet, but we were trying to get away from this reverse return flow and have all of our flow directed to the one manifold location instead of a whole network of header connections. So our consolidated supply and return manifold accommodates the tube and tube, simplifies the horizontal installations, and eliminates the piping arrangements in this figure. So here's a bench scale test that we were doing. So our manifold basically is this block shown on the right side of the table, and we have a 6 foot loops, the coaxial loops. In this case, we did not weld it because we wanted to be able to take it apart. We just used fittings. In the field, we would weld it. And we'll get into that in some of the later slides. We were able to verify that we got equal flow through each of the loops through pressure testing on the loops, and with that ease our concern that we could not equalize flow. But we were able to, and we're not even using valves on this. We're trying to get away from the valves, and we'll talk about that a little bit more later. So on one of the installations we did, we also wanted to know that the pressure drop through the system was not going to be detrimental, and that it would be similar to what we're seeing with the U-tube. And we were able to measure the pressure drop on this installation. That the yellow meter there is the differential pressure sensor, and we were able to confirm that the pressure drop was pretty close to what you'll see in a U-tube arrangement. So now I want to get into the Otisco ground loop system configuration and the components. In particular, we'll talk a little bit more about the manifold. So this is just a schematic on the left showing a typical layout of our system. So we have your heat pump, your flow center in the building, and then our manifold has a supply and return line coming from and to the building, and then we have 3 loops coming off it. So the photo on the right shows what would be supplied if you were to purchase an Otisco manifold, and then it would, of course, come with all the other elements of the ground loop and the supply return lines, etc. And we'll talk about that a little bit more on the later slides. So let's move on to the next slide. So here is a partly assembled manifold with the ground loops on a bench. So we put this together so you could kind of see how it's all laid out, and added the text there to show you supply coming in to the manifold, and then the flow would then carry out through the annulus between the 2 tubes. It flow all the way out to the end of each loop, and there'd be a cap on the end of the exterior pipe, which is 1 1/4 inch, and it would force flow then to go back to the manifold through the interior tube, which goes into the back of this block, and then return flow back into the building. As some of the dimensions of the manifold pit, and some of the loop criteria are shown there. So here are various configurations. Here we're showing what was on the preceding slide. This is with showing an example how we'd use a elbow electrofusion coupler. There's one shown here, two shown on the right diagrams, and then also you see the interior tube. So these tubes would extend roughly 300 feet outward from the manifold, and again be capped on the end, and so the flow would be flowing out of the page, if you will, outward in the loop through the annulus, and then return back near the end point back into the interior tube and flow back into the manifold. As you can see, we have electrofusion couplers. There's two electrofusion couplers that can be oriented whatever direction you need them before you do the weld, and you connect your supply and return lines to those. And then to connect the 3/4 inch into the manifold, there's a fitting where you insert it in, and it connects much like a shark bite that's used for water lines and such in your home. So in this, our goal was to reduce the number of welds, so we only have 5 welds, and they're all done with electrofusion. So 3 straight electrofusion welds, and then the 2 elbows. And that's subject to modification, but that's the arrangement that we're encouraging. So I'm going to rehash some of the details of the ground loop and the components. So just wanted to mention that the manifold that Otisco Engineering has put forward is in patent pending. It was filed in December 2024. It's a consolidated supply and return all in one unit. The loop connections are radially situated on the manifold at 12 degrees from each other, and we've arrived on that through trial and error on some other installations where we did not have it angled, and it just created challenges in the field. You can couple more than one 3-loop manifold together to accommodate a system requiring more than 3 loops. So say you had 5 loops, you would connect 2 manifolds together, and you could cap off one of the ports into the manifold for the unused port on the, so if you only need 5, there's 6 available ports, and you would cap one of those off if you only needed 5. Everything's HDPE, so standard in the industry, as many of you know. Simple connections, 1 1/4 inch exterior tube fused to the stubs. The stubs are about 4 inches long off the manifold, and your electrofusion coupler and the 1 1/4 inch line for the loop are welded with that. For the interior 3/4 inch, you have a retainer and O-rings with locking for the 3/4 inch. Let me restate that. You have retainer and O-rings with a locking ring for the 3/4 inch interior pipe to the manifold. It's standard piping, 3/4 inch, 1 1/4 inch SDR11, and standard electrofusion couplers, elbows and straight couplers. And then these are guidelines, subject to vary based on the design, but the average spacing between adjacent horizontal loops should be 15 feet or greater. We want a minimum depth of 5 feet, ideally greater than 8 feet. Deeper is generally better, but not too deep such that you're unnecessarily increasing project costs. And your depth will depend on climate, soils, groundwater, etc., all the various factors that you need to take into consideration on any geothermal design. So when you're horizontally drilling these, you want to get, down as quick as you can, so the majority of your loop depth is insulated from the atmosphere. Typically, you can get to full depth within about 40 to 60 feet. That's assuming a 10-foot depth. And I'll show you some more in the next slides about that. So here's the next slide. This is an example layout for one of our projects. The building being here, manifold pit. We got as close to the utility room as we could. on the exterior of the building. And the bores were drilled along the alignments of the yellow lines. And these were about 280 feet each. Our general guideline is about 300 foot long, but in this case we ended up 280 feet. And the depth here, illustrated here, it was about 9 feet on the average, or 3 meters. All right, we'll go to the next slide. This illustrates the drill entry angle of 26 degrees, and that's how we arrived at the 40 to 60 feet. Here we're at 43.7 feet for a small rig, entering at 26 degrees. I was able to get down to the full 10-foot depth in that distance. So on the system itself, the interior mechanicals, we're showing here a water furnace 5-series geothermal indoor split unit with Symphony data collection, and this was installed by Weston Air. They're out of Westerville, Ohio, and they install HVAC systems, including geothermal systems. This is a view of the Symphony portal that we utilized on this project. This was a grant-funded project through the U.S. Department of Agriculture. So we were teamed up with Ohio State University, and Water Furnace helped us out a bit on the front end, on the proposal end of the project, and we ended up using their equipment. And so with that came the Symphony portal, and the Symphony portal is we found to be very powerful. Provides a whole bunch of data, but for example, system temperatures and flow rates, control inputs and outputs, energy monitoring, and that's just a snippet of what the power of this system. So we were able to collect data for research purposes. On our first project, we did not have the Symphony portal. We set up our own data collection. First, we won 2 small business innovation research grants, a phase 1 and a phase 2. This is the phase 2. And the first one, we set up our own monitoring for flow and temperature and atmospheric conditions to be able to put together research on it. I'll just keep it simple. But so there was a paper published on that research, and there's another one in the works for the phase 2 grant that we won and worked with Ohio State on. So they were able to utilize the data off the Symphony portal. So here I want to get into some of our installations. So as I mentioned, our latest manifold design that was put in for patent late last year was not what we used all along. So this is going to show kind of the evolution of how we've arrived at the current manifold design and the overall system design. So basically, we've learned some lessons along the way. So this is the Copia Farm. This was our phase 1 grant project. It was a USDA project, so we sought to put the system on a farm setting. USDA is, trying to support the use of geothermal and other alternative energies on the farmsteads. So in this case, we installed it for the farmhouse, and you can see it extends about 290 feet out, and then we have a profile of the drill depth, which, as I recall, was about 9 to 10 feet deep along most of the length of the bore. And here on the lower right, you can see the drill rig that we use. Again, we're seeking to use small equipment, have the least amount of disruption to the properties as possible. And so here was our early manifold. We have valves on it, which we've been, with our continuing design, we've been trying to get away from the valves, and we have. In fact, we listened to an old Dig Deeper webinar from July of 2024 by John Manning of Earth Sensitive Solutions. And in that presentation, he came out with the conclusion that valves are really not necessary for geothermal systems if you design it right. And we've come to agree with that. We had the valves on the project shown here, and with the advancement of our design, we were trying to get the cost down and simplify it. And when you're putting all these valves in, it just adds cost to the project and adds complication. So, whoops, sorry, I didn't mean to turn that on. Let's move to the next slide. So, our next installation, again, we ended up putting in this case, 4 loops. So we weren't yet using our 3-loop manifold on that either. You can see on the next slide that we ended up again putting valves in and welding together various off the market fittings for construction of this system. And one thing I want to state is for each of these installations, we were dealing with trying to bring radially drilled, ground loops that were drilled radially away from the manifold pit and trying to get them straight into the connections. And that ended up being a pain because we'd have to, show on the next slide, I believe, it's not shown here actually. On one of the later slides, it shows how we had to brace the pipes to get them to straighten out to be able to do the welds, which was difficult. This is the same site on the previous slide. We put in some vaults because the owner wanted access to those valves. It's the same site post-installation. We have a small patch of disturbance, and at the far end again, there's small holes that where we came out of the ground. I'll show you that on a later slide. This is the Phase 2 grant project that we teamed up with Ohio State on, and I'll jump to the next slide and show you the details. So this was the Fendrick building at the Molly Cairn Agricultural Center in London, Ohio. This is a multi-thousand acre research facility, and they also have what's called Farm Science Review there every fall, where all the agricultural companies get together and show off their equipment and techniques and tools for agricultural purposes. And so where we installed this system was at the headquarter building, the administration building for that campus. Here we show the tube in the tube. What I didn't mention is we'll pull the 1 1/4 inch tube with the drill rod back through the hole, and then we'll slide in the interior 3/4 inch tube. And this next photo, second from the right, is the 3 tubes before we finished off and inserted the 1 1/4 into them. And here we're doing some thermal testing of the soils. So we have a setup there where we're collecting data on the temperature through one of the loops. And that was a 48-hour test, I believe. And here's the brace I was talking about on the previous slide. So since we splayed outward from the starting point, we had to put a brace on to straighten out the pipes for connection into the manifold. This is an earlier version of the manifold that we've advanced through the help of this grant that we won and worked on with Ohio State. So this is the aftermath. This is the manifold pit location, and then we have supply and return lines going through here. So very little disturbance on the site. There was, small disturbance at the end of the loop. The pipe was pulled back underground. It came out of the ground, then we pulled it back through with the capped end underground. So that was 2 or 3 feet underground at the far end of the loop. This installation was also with Ohio State. It was on the same Phase 2 grant that I had mentioned, and this was a 2-loop system. And again, we're using a small horizontal directional drilling rig, and we used the same block design that you saw in the preceding example project. Here we capped off one of the ends of the loop, so we only needed 2 loops. It was a small research house. It didn't need all that heating and cooling capacity. And this wire here is a locating line that Ohio State required that we put along the loops. So I want to jump into kind of summarize the benefits of the Otisco ground loop system as we see it, as we've concluded through all the work we've done on these projects. So there's only electrofusion welding. I mean, you can do it with socket welding in other ways, but we've set it up so that it's 5 electrofusion welds, simple excavation. There's a material cost reduction. You only have the 5 fittings, and the site restoration will be a lot less than other types of designs like shown in the photos earlier. Again, minimally invasive, small ground impact, perfect for retrofits. There's a time reduction. Once, there may be a learning curve on your first project or two, but after that, we think these systems can go in a lot quicker than vertical installations where you have to trench the pipes together and so on. And then the retrofits, easy for retrofit. You saw that first example project early on where we were able to do it right between the houses. And a simple field installation process with the 5 welds and a brief training. So we believe this is the way to go on, not every site. Every site's different. There might not be space for horizontals. You might be dealing with bedrock you don't want to deal with, but in Ohio it's worked well where we have deeper soils, and I'm sure there's plenty of places across the U.S. where it can be applied. So aside from the benefits of our system, there's been other benefits in the work we've been doing with Ohio State, water furnace, and teaming up with local contractors and so on, educating them on geothermal. So, we're trying to advance geothermal. Hopefully the Otisco ground loop system will catch on, and others will be able to utilize it and reap the benefits. So that's our presentation. If you have any questions, we're open. So I imagine, are you going to read them off, Greg, or how does it work from here?
Yes, I will read them off. Yes. Okay. Well, very good. There were several questions, so we'll start with the first one I saw. This is a question from Jordan Gershberg, and Jordan was asking how many wells and how much capacity could be achieved with your Otisco system.
I'm going to let Greg Nortz jump in on answer that one. He has to unmute, so just give him a second.
Oh, there we go. Basically, we focused on a 3-ton system with our manifold because it would probably be the largest market. But you can, I'll call it daisy chain them and get up to a 6-ton with this system, utilizing the 1.25 inch supply and return lines back to the building. But if you distribute your heat pumps throughout a building, you could do as many as you need, obviously, which is, I think, from a design standpoint and working in the HVAC industry for some time, is a trend that's people are moving towards, because you distribute, you don't have as much ductwork to deal with, and so on and so forth. I hope that answers your question.
Okay. Yeah, I think so. All right. Very good. Thanks, Greg. Next question was actually 2 or 3 questions from Jeff Volmer. Jeff is asking, what is the depth of the pipe installation, and what's the rule of thumb, like for a linear foot per bore per square foot of building? Do you have that type of recommendations or data that people could use on their design?
Yeah, I'll take that one on as well. In the HVAC industry, there's all kinds of rules of thumb as far as square footage. There's always the 400 square feet per ton for cooling is a common one, but you should do manual J and figure out what your real heat loads are on your building. And then as far as how many lineal feet you'll need per ton, another rule of thumb is about 300 feet per ton of ground loop will provide your heat exchange required to heat and cool a building. But there again, it depends very much on your ground conditions, such as the water. You know, how is it sand? Is it clay? As far as how much heat exchange you'll get from your each loop. But yeah, there's all kinds of rule of thumbs out there, but you've got to be careful, and you have to do your measurements, your thermal conductivity measurements on your loops to determine what the actual heat exchange is for a loop. And then on the buildings, again, you know, run your calculations to determine your heat loads and your cooling loads required. So the answer is it depends, of course. Okay.
So it's very subjective to the application and the conditions that you're going to have at the site. Very good. His next question was regarding cost. So he was wondering if you had some kind of an idea on cost per foot of bore for your loop system design.
I hate to quote, you know, real numbers that you can utilize for any installation on any site, because they all differ again, and it depends on your site conditions. It depends on your building and how much you're heating, of course. But I guess if you're looking at a 3-ton system, I think you're in the range of about $25,000 to $30,000 for an installation of that sort. That's what I've seen in the marketplace.
Okay. All right. Yeah, I think it definitely varies by your local cost and conditions. Yes. So yes. Again, it's probably a subjective.
I'm going to add, since this is a new thing, a new way of doing things, there's not enough data points to really get a good handle on the numbers. But we believe that based on what we've seen, that we can put these in less expensively than horizontally drilled system with headers.
Mm-hmm. Okay. And he had one last question. What was the largest building that you've done so far with your system?
Probably the Westlake installation.
Okay.
That was one of the examples that we had there.
Okay. All right.
And I don't know the square footage. It was probably on the order of 3,000 square feet.
Okay. All right. Looking through, there's several more questions coming in, which is great. Keep bringing your questions if you have them in the chat. The next question I see is from Ruben Arleno. Hopefully I got that right, Ruben. He says, great work. Have you looked at doing vertical installs with inclined boreholes from a central hub with your technology?
We've talked to people about it. It's possible. There's no reason why we can't modify, what we call the Otisco ground loop system to connect our manifold to slanted borings. It just takes a little more thought, because it was designed with the more horizontal alignment in mind.
Mm-hmm. Okay, sure. All right, fair enough. Next question from Trevor Wingle. Trevor asked, do you grout the horizontal bores, and how do you get good conduction to the ground?
I'll take that one on. There's been, between Pat and I, we have discussed it and looked and read and researched it significantly, and we found all our installations we have not used grouting, and the performance has been more than acceptable. But there again, it depends on your ground conditions. Because we're going in with a smaller bore, like a vertical bore would be a 6-inch bore, and then you'd put your U-tube down into that bore. You have a lot of open space. So grouting is you always performed on that.
Yeah, let me cut in on that too. I mean, on a vertical bore, you have to, just for contamination prevention, migration issues. On a shallow 8-foot bore, it's not as vital from that standpoint necessarily. I mean, it could be, but anyway, keep going, Greg.
Yeah, Pat's the geologist, and he understands that you don't want to transfer any contaminants from one region to another on the vertical. On the horizontal, you don't have the same situations. And we found that the hole does collapse on the pipe, and even if it doesn't, you're still going to get significant heat transfer through radiation. It will still transfer heat from the pipe to the surrounding area. Whether you have conduction or radiation, you still will get significant heat and probably enough heat transfer to make the system work adequately. Grouting, yes, it's an expense, but is it worth it? So far, we haven't shown that the expense is worth the extra performance.
Okay. Excuse me. All right, very good. We got a couple more questions coming in. So Robert Washburn's asking, when you insert the internal return pipe, how do you know when the pipe is fully inserted into the manifold?
Well, you have a cap on the end, and it hits the cap, and you also have to track the length of your pipe so you know that you're close. So you're going to have your pipe pre-cut to the length plus some, because you want a little extra to be able to cut off and size it up with your manifold. But so that's generally it. You track the length. Typically, there's graduation markers on the pipes. You want to. There's some care that has to be taken there, but you'll feel it when it hits the cap, typically, and then you pull back a little bit so you're not snug up against the cap.
Okay. All right. Next question. Lance McNevin is asking, how is the manifold block manufactured to be hollow inside? Is it welded from HDPE sheets or machined from a block and then welded, or is it rotomold?
It's machined.
We used a horizontal milling machine to provide the openings in a block of high density polyethylene. We've also looked at 3D printing, and we have 3D printed a couple models, and we also are going to be looking at possibly other manufacturing methods. But today, in our initial production runs, it's been a horizontal milling machine that we've utilized to provide the final design.
Okay, very good. Next question from Pete Preidebeck. So when using currently available loop sizing programs, like most of the manufacturers have, how do you account for the coaxial length with those software programs? Any experience with those type of things yet, guys?
Well, we haven't plugged them into those programs. What we've been using, and I can't speak for the models that Ohio State's been using because I don't remember the names of them, but they're modeling sophisticated models, I'll call them, to demonstrate the heat transfer, and they've also looked at sensitivity analysis on increasing the exterior pipe size, modifying the loop length, varying the soil, thermal conductivity parameters, a whole bunch of parameters, and that's demonstrated in one of the publication that I showed on the slide that preceded this one, and that's available to review. And then that was done at our phase 1 grant site, and then they're doing similar modeling and evaluation at the phase 2 grant site. But in terms of putting it into the standard industry models, we have not done that yet.
Okay.
Yes. The graduate student did model it using an ANSYS program and came up with some interesting results showing that from a length standpoint, in those pipe sizes, it optimized itself somewhere around 270 feet as far as where you got the biggest bang for your buck on your length. So after you got longer than, say, 300 feet, your return on the cost of your material and the cost of drilling was not as efficient, or is not as high as you were at that first 300 feet. So, and he also modeled in that the flow rates and the types of fluids that you would utilize to determine your performance. So it's a very interesting paper, but yeah, it's not a standard in the industry, of course, as of yet, but could be utilized as more models are built.
Mm-hmm. Okay. Pete had one more question. He was asking, how do you keep the inside pipe equally spaced through the circuit?
We don't. Short answer is we don't. We decided you're going to have the same area. If your one pipe, say it's slightly resting on the bottom of the other pipe, you still get the same area as you would if you centered it. And we actually sought out a patent in the early 2010s, and we were looking at every gadget out there for spacers and all these things to try to center it in the pipe. And we came to the conclusion that we don't think all of that's necessary. So I don't know, Greg, if you want to add anything to that.
Yeah, that kind of makes
Greg
sense
Nortz.
to me, I guess.
Yeah.
Because it's very small surface area where it does touch, and the whole thing's flooded around it, so it probably makes sense to me. From my technical viewpoint, I think that would make sense.
I was asking for Greg Nortz's thoughts if he had any more.
Oh, I'm so sorry.
That's all right, but thank you, Greg Kurtz.
The tubes will touch at certain points along the length, but the critical heat transfer from the ground around it to the fluid inside is what's the most important part. And as far as the amount of heat that is transferred, so it's not significant, the touching of the tubes, from what we've tested. And we did, as earlier shown, we did the U-tube versus the tube and tube side by side, and the performance of those were nearly identical. So
Okay.
it substantiates, that it isn't that important. Okay.
Okay, we're getting close to our time. I got one last question, looks like, that's in here. So we'll take that, and that might wrap it up today. But this is a great question, I think. A lot of folks, particularly who've not done horizontal bore drilling applications, might be more interested in this. But question from Stephen R. is, how many large boulders have been handled when horizontal drilling? So like, I assume he's talking about running into large stones, rocks, boulders, obstructions in the earth that you might encounter as you do that run out with that machine.
Well, it makes the drilling a lot slower. You want to avoid those. When we did our first bore at the residence, I think we went through an ancient stream bed with the bore, and he did hit a lot of those, and it did create havoc. So he backed up and went above or below. But yeah, if you can avoid the boulders, yeah, that's going to cause a problem vertically or horizontally. But yeah, you don't want to have to deal with that situation if you can avoid it. I don't know how else to answer that.
Typically, you can back off and it'll skate around it. You might not go in the direction you want for a portion of the hole, but usually you can correct it after you pass. If you hit a very large boulder, well, I can't speak for that. We might have to just move the borehole location.
Yeah. Okay. All right. Well, we're at the top of the hour here, so I think we should wrap it up. Thank you both for your presentation and your material. I think it's very interesting what you're doing, and I'm hoping our viewers and